Hi there, and welcome to the sixth video in our Unit 1 Integrated Math series on polynomial functions. Really, this unit is also about analyzing graphs as well, and we're going to get into more of that today. But as always, let's start with our mental math, or warm-up for today. So our 6 problems here on the board, some different problems than maybe what we've looked at before, but go ahead and take a second to see what you can do on these. All right, so let's take a look. Number 1 here, we've seen a problem like this before. 16 over 7 times 21. As we said previously, we can divide by 7 first and then multiply by the 16. So 21 divided by 7 is 3. 3 times 16 is 48. Number 2, increasing 61 by 5%. So if you want to increase by 5%, that's 105% of the original value. So really, you're taking 105% of 61 there. And you could do this in 2 steps. You could take 5% of 61 and then add it to 61, or just take 105% of that. So really, it's 105%. 105%. So let's multiply 105 times 61. So it's going to be a little tricky here. So let's see. We've got 60. Let's just do 60 times 105. So 60 times 100 is 6,000, and then 60 times 5 is going to be 300. Add those together, you get 6,300. And then 105 adds 105 to that. So that's going to be, because we're just taking the numbers involved. I know it's going to be like 1.05, but we're taking the numbers involved as always, and then we're going to adjust the decimal later. So so the 1 times 105 would be 105. Add that in, and you get 6,405. Now, we're going to need to adjust the decimal because obviously 6,405 is not just a 5% increase. So is it 640.5? No, still too much. How about 64.05? That makes a lot more sense. All right, so 64.05 is our answer there. And if you needed to use a calculator on that one, that's perfectly fine. That was a little bit more challenging than maybe some of the other ones that we have done. What degree is this polynomial down here, as we've studied before with factored form of a polynomial? This one, let's see, we've got 1 factor of x here. We've actually got 2 here, so that makes 3, because that's squared term. So we have 1, 2, 3, 4. So if we were to multiply that all out, we would get an exponent of 4, highest exponent of 4. So this degree is 4, or what we call a quartic function. All right, number 4. If you notice, the x's both have a coefficient of 1. So if we were to use something called elimination, if you remember that from integrated 1, elimination, we can actually subtract our 2 rows. So if we subtract x minus x is 0, 3y minus 4y is actually going to be turned into a plus 4y, so we get 7y. And then 29 minus 8 is 21, so y ends up being 3. And then of course we can substitute that back in to find x. So if y is 3, then we're going to have x plus, let's see, 3 times 3 is 9, if we substitute that back in there. And then x is going to end up being 20. So if we were to think about the intersection of those 2 lines, they would intersect at the point 20, 3. And then next, number 5 here, we're solving for x there. And there's really not a whole lot of algebra to be done here. It's simply using our reasoning skills, our mental math skills, our knowledge of exponents to solve this one. As we've talked about before, anything raised to the 0 power is going to be 1. So we just need to think about what value of x makes that exponent, the whole thing, 0. So if we substitute -5 here, -5 plus 5 is 0. Anything to the 0 power is 1. So it actually didn't matter that this was a 3. That could have been any number right there, except for 0, and it would have worked out the same way. So x is -5. Number 6, factor x squared minus 6x minus 40. Again, we want to think of two factors here that when we distribute out would give us this back. So x times x would give us this x squared. And then think about the next two things here. This one times this one, and then this one times this one. Those are both going to be linear terms, so we want those to add together to give us our linear term here. So these two numbers right here have to add to give us -6. But then the last thing that we would do in the, if you want to call it FOIL process, is this part here. They have to multiply to give us this last one. So we need two numbers that add to give us -6, but then multiply to give us -40. So let's think about that. Let's see, factors of 40. So what two numbers multiply to give us 40? You've got 8 and 5. Are those going to add? 8 and 5 going to add to give us -6? Or maybe positive 8 and -5 still doesn't work out, right? So let's think about another one. How about 10 and 4? 10 and 4. I think that's going to work. So I have to do a -10 here and a positive 4 here. So when we were to distribute this out, we have x times x is x squared. X times -4 or positive 4 is 4x. And then x times -10 is -10x. Add those together, you get the -6x. And then -10 times positive 4 is -40. So just to reiterate there, how to factor a quadratic with a leading coefficient of 1, we can just kind of think through the reverse distribution there. All right? So let's go ahead and move on to our lesson for today, which is on average rate of change. And we'll talk about what that means as we go. So this is our goal for today, is to calculate average rate of change of a nonlinear function. So a nonlinear function is any function that's obviously nonlinear, meaning it does not follow a constant rate of change. It's not a straight line, in other words. Interpret and compare positive and negative average rates of change, and we're going to look at that in the context today. So here's our context. So we have a bicycle traveling at a steady rate and a truck are moving along a road. The graph below shows their positions in feet from the start of the road as a function of time in seconds. Let B of t represent the bicycle's distance and K of t represent the truck's distance. So I'd like for you to do for just a moment is think about which one of these represents the bike and which one represents the truck. So take a moment. Okay, so in the description up here, it says the bicycle is traveling at a steady rate or a constant rate. So as we talked about before, that's a linear function. So the bicycle is going to be represented by this straight line right here. So that is B of t. And then of course, that means the other one is the truck. So this is at a non-steady rate, this truck here, as it follows the path there. So that's K of t. So what I want to give you a chance to do is think about like, what is going on here? Thinking of like a story that represents, that can be represented by this graph. So right here we have time in seconds. So it all goes all the way to about 35 seconds. And then this one is distance away from some starting point. So they're following along maybe the same road or something like that. So this is the distance along that road away from a particular starting point. So take a moment, see if you can come up with maybe a story that represents this graph here. Okay, so I've had a number over the years, a number of students come up with different stories here. One of my favorites is the bicycle and the pizza delivery guy. So this is a bicycle here, obviously, as we said before, and then here's a truck, and he's trying to deliver a pizza, and they're racing. Okay, so the bicycle is on the side of the road, on the bicycle path, and so he doesn't have really a whole lot of restrictions. Whereas the truck has to stop for different things and worry about the other cars that are on the road and that kind of thing. So the bike kind of gets a head start here and is moving along the road, and then the truck, because the truck is faster, kind of increases really quickly in here. It's traveling at a really quick rate here, and then kind of slows down and passes the bicycle at that point, but then has to slow down and eventually stop. So the truck is stopped here at maybe a stop sign or something like that. So because of that, the bike continues on and passes the truck. But then once the truck passes through the stop sign, he speeds back up and goes really, really fast through here. Notice that he's traveling faster here than the bike is. So, because it's steeper here than maybe the bike is. So he passes the bicycle once more, and then at the very top there, he actually delivers the pizza. And because he's delivered the pizza, he's like, I'm not worried about this race anymore. And he actually, he doesn't slow down here. This maybe is a confusing part of the graph. He doesn't slow down there. He actually turns around. And he heads back towards, because the distance away from that starting point is decreasing. So he's actually turning around, heading back to where they started from. He didn't slow down. He didn't fall off a cliff or something. This is distance away from the starting point. And so he turns around and he heads back towards maybe the starting point or his pizza business or whatever it may be. And so there's lots of different ways to analyze this and come up with different stories, but that's one that's been shared over the years. So it's important to notice a couple of things here. One is sometimes the bike is traveling faster than the truck. Sometimes the truck is traveling faster than the bike. And then if it's decreasing, as we've talked about in the last couple of videos here, if it's decreasing, it's actually turning around, going back towards the starting point. So a number of things to look at there. Let's start with a couple of questions here. Now that we kind of have dissected this graph and kind of thinking about what is actually happening here. So number one, it says a student named Jack claims that the average rate of change for both the bike and the truck is the same in the first 13 seconds of travel. Do you agree or disagree? So is the average rate of change for both the bike and the truck the same for the first 13 seconds of travel? So from here to there, is the average rate of change of the two the same? So I know we haven't talked about what average rate of change means yet. Maybe you've learned about it in previous years, but just take a moment to hypothesize. What do you think? 0 to 13 seconds, are they the same or not? Okay, so let's kind of think about what average rate of change is. So let me go back to here. Average rate of change is the change in quantity over change in time. Change in quantity over change in time. So let's use that part of the definition first. We'll come back to the other one later. Change in quantity over change in time. So in this case, we're talking about change in distance over change in time. So if we go from 0 to 13 seconds, so I can see why Jack's thinking that, because they start and then at 13 seconds, they're at the same distance away. Right? So he's like, okay, they travel the same distance over the same amount of time. But did they? If you look at the very start here, the bike actually got about a 20-foot start here. Head start. Ahead of the truck. And then at 13 seconds, they're at the same position. So did they travel the same distance over the same amount of time? They did not. Because the truck actually had to travel further to get to 280 feet than the bike did. So the truck actually had a greater average rate of change in between 0 and 13 seconds because of that. All right? So average rate of change in this case is distance traveled over the change in time. All right, so let's actually mathematize this for just a moment here. So let's do the bike. So the average rate of change for B of t, the bike in this case, change in distance here would be, let's see, 280 is where they finished. So 280 minus, where did he start? About 20 feet? Divided by the change in time, which would be 13 minus 0. So we're doing change in distance, 280 to minus 20, that's a change of 260, divided by the change in time, which is this distance difference here, which is 13 minus 0, so it's 13 seconds. So we get 260 divided by 13. Mental math here, 26 divided by 13 is 2. So 260 divided by 13 is 20. So 20 feet per second is the average rate of change of the bike over that interval. What about the truck? So K of T. So K of T. 280 minus 20. Actually minus 0. I'll get it right here in a second. Divided by 13 minus 0. So the truck here, 280 again, minus, where they start 0, divided by 13 minus 0. So you can see here, it's going to be 280 divided by 13, which is going to be 21.5 about feet per second. So approximately 21.5. So as we said a minute ago, the truck has a greater average rate of change over that interval because it traveled more distance over the same amount of time. So it had a greater average rate of change. So when we think about average rate of change in this particular scenario, we're talking about change in distance over change in time. We're really talking about speed, but even more so velocity. So there's a difference between speed and velocity. Speed is just how fast you're traveling. Velocity has a direction attached to it. So for instance, if I start here and I travel this direction, I've got a positive velocity. But if I head back towards that starting point, that initial point here, I've actually got a negative velocity now. Whereas if I'm talking about speed, I've got a positive speed going there and back. But velocity has a direction attached to it. It can be positive and negative. So when we think about average rate of change in this particular scenario, we're talking about more so velocity than we are speed, because of if you think about this scenario here where he's traveling back towards the pizza business, he's got to he's going to have a negative, because it's decreasing. He's going to have a negative average rate of change in that particular case, which we'll talk about here in a minute as well. So that's the key there is change in distance over change in time. So do we agree or disagree? We disagree, and we looked at a number of reasons why that was. State time intervals when the bike and truck have the same average rate of change. So they didn't between 0 and 13 seconds, but over what intervals do they have the same average rate of change? So take a minute to think about that on your own. When do they have the same average rate of change? So I'll give you a second to do that. Okay, so there are a few instances that are easier to see than others. For instance, between 7 seconds and 13 seconds. That's one that's fairly easy to see because they start at the same distance away from the starting point and they end at the same distance away over the same amount of time. So they're going to have the same average rate of change. We don't even need to calculate it because they travel the same distance over the same amount of time. Another one might be 13 seconds to here, which is about 23 and a half seconds. They have the same average rate of change over that period of time as well. But it doesn't have to be where they intersect. Let me give you an example of that. How about 0 to 14 seconds? So they did not have the same average rate of change between 0 and 13, but what about 0 to 14? Well, they don't intersect there. But the key here is, did they travel the same distance over the same amount of time? So it looks like the bike is about 20 feet ahead of the truck here. Where do you start? Oh, we started with the bike being 20 feet ahead of the truck. So they traveled the same distance over the same amount of time because the bike is still 20 feet ahead of the truck. We could do the calculations and I'll leave you to do that, but they have the same average rate of change over that period of time because they traveled the same distance over the same amount of time. Let me give you one more example here. How about, let's see, 0 to 6. 0 to 6. Same thing, right? The bike is still about 20 ahead of the truck, and so yes, they've got the same average rate of change in that interval there. So you can see that there are a number of different cases in which that would happen. All right, let's go ahead and go on to number 2 here. Are there any time intervals on which the average rate of change of the truck is 0 or negative? What's the actual speed of the truck during that time interval? So explain your reasoning. So let's go back here and look. Where is the average rate of change of the truck 0? Where is it negative? And maybe thinking about why. So take a second to do that. All right, so the average rate of change of the truck is 0 whenever the truck traveled a distance of 0 over some time interval. And one of those cases would be when he stopped at the stop sign. So from 13 seconds to 18 seconds. So change in distance would be 0 over change in time would be 18 minus 13 is 5. 0 divided by anything is still 0. So this would be 0 feet per second. So in that time interval, his average rate of change there was 0. But there are others. How about from 18 seconds to 35 seconds? That's a weird concept because he did travel at that in that time interval, but in terms of his position, like he started at 280 feet away from the original starting point, and he ended 280 feet away from the starting point. So his distance traveled over that time would be 0 still, divided by the change in time, which is 35 minus 18, which is 17. So we 0 divided by 17, which again is 0 feet per second. So kind of interesting there to see that. Really what we want to know here is when is what we call the secant line. So it's a line segment joining 2 points. When does the secant line have a slope of 0? So really we could come up with a number of these, right? From here to here, that would be an average rate of change of 0. Here to here. It doesn't really matter where we put it along this this curve here. It's going to have a average rate of change of 0. So I wanted to introduce this kind of new idea here. Is the slope of this what we call the secant line. So let's go to our second definition of average rate of change. So we have change in quantity over change in time. Yes, we kind of talked about that, but you can also think about it this way. If a situation followed a linear path instead, so obviously this truck is non-linear, but if it did travel a linear path in some time interval, what would the rate or slope of that line be? So this is what we call the secant line. So we really want to know is, in terms of the average rate of change, is what is the slope of the secant line? And it won't necessarily be the slope of the actual line, but that still tells us, on average, how quickly things are increasing or decreasing over this time span. So you might think about a business and profit, and maybe they have an increase of profit one day, a decrease next, a really large increase the next, stayed steady the next day, and then it kind of varies. Well, what on average what are they doing by day? And so they can take the total profit from day 0 to day 10 or whatever it may be, divide by 10, and then you can see, like, on average, what should we expect to increase or decrease on any given day. So over that time span, what was the average rate of change in profit? So the secant line here, it's actually the whole theme of this whole task is thinking about the secant line. Because in many ways, the bike represents the secant line for the truck, right? So from here to here, from 7 seconds to 13 seconds, if we think about the average rate of change of the truck, really it's just the speed of the bike. So instead of calculating the average rate of change of the truck, we can just say, okay, well, what's the slope of this line here? What's the slope of the bike at that point? Of B of t. And so really anytime, and it doesn't have to be limited to just the secant line that's formed with the bike here. But you could say, okay, what is it from 18 seconds to, what is this here? 25 seconds. Well, that's the slope of this line here, which of course will be change in y over change in x, which is really just the change in the quantity over the change in time. And so but you can think about visually, it's the slope of that secant line. So this is going to be positive here. In fact, from 0 seconds to about 28 seconds, anytime in there, the secant line is going to have a positive slope, except for maybe in this little window here. But if you go from any 2 points in that interval, so from here to here to here, here to here, here to there, here to there, there. I mean, and any ones within that. So you could start at any point here. And we could calculate the average rate of change between, 6 seconds and just over 21 seconds. We could calculate that just by looking at that slope there of that secant line. So I know this is kind of a difficult concept to grasp, but let's look at it in a number of other cases as well after we finish this one. But hopefully that kind of gives you a way to visualize average rate of change. And of course, the average rate of change will be negative if you start at some place and end below it. So that's kind of a negative average rate of change, which would represent the velocity in this case, because over that time span, he was heading back towards the start. So yes, there are time intervals in which the truck has our average rate of change. 0, negative, what's the actual speed of the truck? So the actual speed of the truck will be the absolute value of the velocity. So if it happened to be negative, average rate of change, the speed would actually be the positive of that. So that's the difference, as we said before, between velocity and speed. All right, and then lastly, in what 2-second interval is the magnitude of the average rate of change, so the absolute value of the average rate of change, the greatest? So when in other words, when was the truck traveling the fastest? Okay, in terms of speed. So I'll give you a second to think about that. Okay, so if you look here, we're looking for the steepest point of the graph. Again, 2-second interval. So over what 2 seconds was the graph the steepest? And you could maybe think maybe between 6 and 8 seconds, because it was pretty quick in here. Between that point, he traveled 120 to 220, so maybe 100 feet there. Where else is he traveling really quickly? So you can see here, it's pretty steep in here, but it looks even steeper over here. Between 33 and 35, he traveled much more than 100 seconds. And that's going to end up being the one there, from 33 to 35 seconds. And you can write that in interval notation if you want. 33 to 35 seconds is when the speed of the truck was the greatest. Even though he was traveling back towards the starting point, So his velocity was negative, but that's when he was driving the fastest in terms of speed. Okay. All right, so let's take this idea and let's apply it to a newer novel situation here. So we've got this polynomial. We've been studying polynomials, right? This is a quartic. And one way to recognize a quartic is to count the crests or troughs here. So there are 3 changes in direction, and the degree for a polynomial will be at minimum these number of changes in directions plus 1. So we've got 3 changes in directions plus 1 would give us 4. So it's a quartic, most likely. Okay, it could be something higher than that, but at minimum, it would be a 4 or quartic. Okay, so let's see. Number 1, estimate the average rate of change of y over the interval from -10 to -8. So from -10 to -8. Estimate the average rate of change. So take a second to try that. Okay, so we're looking at again, change in a quantity, or in this case, just change in y over change in x. So it's really just the slope between these 2 points here. So the change in y, so that it went up 8, right? Up 8. Over change in x, it went to the right 2. So that would be 4. I mean, you could do y2 minus y1 over x2 minus x1 and all that. But really, just if you can visually see the change in y over the change in x, then you don't need to write that all out necessarily. All right, so that was 4. For what interval, -10 to -8, or 4 to 8, is the average rate of change greater? Explain. So from -10 to -8, we just did that one. I'll draw the secant line here. It looks very similar to the actual line, but it's not. If you were to zoom in, it'd be different. And then from 4 to 8, 4 to 8. Okay, those look really close there. I can't really tell if one's steeper than the other one, so I don't know which average rate of change is greater there. So let's do the math for the second one and see. Okay, so the change in y, so it increased from here to here, increased 14, right? 0 to 14. So the change in y is 14. Change in x, which is this distance down here, it went from 4 to 8, is 4. Okay, so if we divide 14 by 4, let's see, let's compare it to 4 over here. If it was 4, this would be 16 divided by 4, but it's not quite 16 over 4, so it's going to be, we don't know exactly what it is. It's going to be same thing as 7 over 4, which is a little bit under 2. So it's going to be less than 4. All right, so the average rate of change for -10 to 8 is actually greater than from 4 to 8. Number 3, over the interval from 4 to 8, does f of x or g of x? So f of x is the one graphed here. G of x is given us in a function form down here, have a greater average rate of change. Show your work. Okay, so we know that this one is, let's see, 7/4. So that's going to be 1.75. And then let's look at g of x down here. From 4 to 8. Okay? So we want to think about what's the point at this function at 4 and what is it at 8. So let's do some math here. So if we substitute in 4 for x, we can see what the y value is at 4. So it's going to be 16 times 2 is 32, plus this is going to end up being 3 equals 35. So we have the point 435. And then when we substitute in 8, I'll do that in blue here. 2 times 8 squared will be 64 times 2 plus 8 minus 1. 64 times 2 is 128. Plus, this is going to be 7 equals 135. So we have 8 comma 135, so we can do the average rate of change now. So again, changing y over changing x. From 35 to 135, you're going up 100. So that'd be 100 divided by the change in y, which would be up 4. So you have 100 divided by 4, which is 25. And obviously 25 is a lot greater than the 1.75 we got up here. So we're going to go with g of x having a greater average rate of change over that interval. All right, so we've seen it graphically. We actually had to figure it out here with just a function, or we can just substitute the values in and find the slope. But what about a table? So this last example talks about average rate of change from a table. So we got some new values here from this new function, h of x. The average rate of change of h of x over the interval from 1 to 3. So from 1 to 3, the average rate of change is -5. What is the missing value in the table? So this time we're going backwards. We don't have all the data and looking for the average rate of change. Now we don't have a particular point. We're looking for the average rate of change. So kind of going backwards a little bit in terms of what we're looking for. So if the average rate of change is -5, so again, think back to our definition of average rate of change. If this data were to follow a linear function or a constant rate of change, it would have a slope of -5. That's what we know about this. Now, does it follow a constant rate of change? No, right? You're going up 3, and then this last one's like up 34 or something like that, right? So it doesn't follow an average rate of change or a constant rate of change. But we're saying if it does follow an average rate of change in between these two points, the slope would be -5. Okay, so what we can do is let's just assume it travels at an average rate or a constant rate of -5, and let's just see what happens. Okay, so we're not even going to look at some of these other numbers involved, like this 6 here. This 6 doesn't matter, right? Because we don't really factor in stuff that happens in between. We just think about where we start and where we end and what's the slope there. Okay, so from 1, 3 to 3 comma question mark here, the slope should be -5. So meaning every increase of 1 in x, it should go down 5. Okay, so from this point here to here, if it were to follow a constant rate of -5, the next point would be 2, -2, right? Going down 5 from 3. Okay? If you go down 5 again, you'd be at -7. So if we were to follow this constant rate of change of -5 over that interval, it would be -7 at 3. So our answer here is -7. Let's just check it to make sure. Okay? Average rate of change is really just the slope between these 2 points, the slope of the secant line between those 2 points. So it would be, actually change in y would be -7 minus 3 over the change in x would be 3 minus 1. Let's see, -7 minus 3 is -10. 3 minus 1 is +2. So you get -10 divided by 2 is -5. So that checks out, right? So -7 indeed is that value in the table if the average rate of change in between those 2 points is -5. So I know it's a little confusing. There are other ways to do this type of problem, but to me the easiest way is just to go down, start from the first point, and go down at a constant rate until you get to that missing value and find out what that value should be. All right, what is the average rate of change of h of x over the interval from 2 to 7? So 2 to 7. So let me erase all my work up here. So from 2 to 7. Okay, so we're not missing any values in the table. When you want to calculate what would the average rate of change be. So if we were to follow a constant rate from here to there to there, to 5, 6, 7, what would that constant rate be? Okay, so let's calculate the slope of the secant line between these 2 points. So 46 minus 6 over 7 minus 2. 46 minus 6 is 40. 7 minus 2 is 5. And we get 8. And we could substitute in or put in our units if we had any. So the average rate of change here between 2 and 7 is 8. Now does it follow that constant rate? No. But we're saying on average, the average rate of change is 8. So if we were to follow a constant rate, it would be 8. So it gives you some good things to think about there. All right, so we've seen it in a graph. We've seen it in a context, and we've seen it from a function, actually, that one time. And then now we've seen it from a table. So hopefully this idea of average rate of change is starting to settle in a little bit. I know it's a difficult concept, but really it's just the slope of the secant line or the change in quantity over change in time. All right, so hopefully we've been able to reach our goal for today. Again, these two here, calculate average rate of change of a nonlinear function. Remember, just the slope of the secant line. Interpret and compare positive and negative average rates of change, which we did quite a bit with the bike and truck example. So with that, I'll say goodbye from this video, and I hope to see you next time.